After discussing tons of properties of the circular bar, now let's derive the elastic torsion formula for a circular bar. Consider the cross-section. For each element in the cross-section, there is shear stress, tau. For an arbitrary element on the surface, it has a distance rho from the center line of the cylindrical prismatic bar. Since for the entire chapter we are talking about there is a torque acting on the cross-section, therefore we also need to find the differential form of the torque such that we can sum up the torque for every differential area element on this surface. The differential torque of an element on the cross-section dt equals to the shear stress tau times the differential area, so those two terms multiplied together generates the force, which is dF. Then we times the differential force by the distance rho from the centroid to get the differential torque, which is given by tau rho dA. Next, we substitute the relationship between the shear stress and the maximum shear stress into it. The differential torque can be rewritten in this form. Then we do the integration on both sides, and we also take this constant out, such that we get this result. Now we define a quantity called the polar moment of inertia, which is given by the integral of rho squared dA over the entire region. Then the torque can be written as T equals to tau max J divided by R. However, although we get this result, who knows what is tau max, right? We don't know anything about it. We cannot observe it directly from the shaft. Therefore, our ultimate target is to express the torsional deformation in terms of applied torque. Consider the tau max, since we know that, so the maximum shear stress inside the shaft is given by G times phi divided by L times R. Therefore, we substitute this stuff into the tau max, then we get this. At the same time, we can cancel the R out, such that eventually we get T equals to G phi J divided by L. Finally, we rearrange the terms such that we make the phi to be the subject of this equation. Then we get the elastic torsion formula, which is phi equals to TL divided by GJ. Notice that it is rather comparable to what we have learned before, which is the axial deformation of a piece of material under the axial load. Delta equals to PL divided by EA. So in such case, P and T are loads acting on the prismatic bar. L are the length of the material. G and E are material properties. J and A are sectional properties. So as you can observe, they are rather similar and comparable. It is an extremely important result that you will frequently use in a lot of applications about the pure torsion. It will be illustrated in the examples.